The science of astronomy sprang from necessity, the need of the ancients to measure time, to know the date. The movements of the moon, the sun, and the stars made it possible. A calendar was set by the cycles of the heavens. Today, astronomy means discovery, the quest to understand the nature of all that exists, to comprehend the universe. To observers of old, the Earth was at the center of the universe. Today's stargazers know how insignificant we really are. The path to that self-awareness is the history of astronomy. Observatories are as old as civilization. This Mayan pyramid in Mexico was a line to register the sun at the equinox. Stonehenge in England dates from 2900 BC. And from even earlier, this great tomb in Ireland. It's so constructed that only on the shortest day of winter can sunlight shine directly inside. Even today, we measure time by the stars. It's done with a series of pulsars. Their spin is used to regulate the beat of the most accurate atomic clocks on Earth. From more than 30,000 years ago, timekeeping by the moon. A remarkable record carved on reindeer bone. Day by day, it seems to show the phases of the moon. A graphic record of that calendar in the sky for the intelligent prehistoric observer. The point on the horizon where the sun rises alters every day. It's the combined effect of the daily rotation of the Earth and its annual orbit of the sun. To ancient horizon observers, twice a year the sunrise point would virtually stand still. These times they recognized as midsummer and midwinter, fundamental markers in measuring the seasons. As the sunrise point began to move again, they knew the season was on the turn. The world over, the earliest observers used the sun as a calendar. In this Native American cave, an arrow of sunlight indicated midwinter as it hit a calibration on the wall. Much older is this burial mound in Ireland, a Stone Age marker of the winter solstice, and so constructed that the sun would shine directly in here just once a year. It happens on December the 21st. On a grander scale and younger vintage, these are the famous temples of Abu Simbel in Upper Egypt, twin markers of the rising sun. But Stonehenge in southern England is the most famous of all, a megalithic observatory par excellence. Its key alignment is here, from the center of the stone circles, through the heel stone beyond to the midsummer sunrise. A moment of awe, the summer solstice from the heart of an astronomical computer that's been spot on for 5,000 years. So complex are the stone configurations, it's been suggested Stonehenge could predict solar eclipses. That degree of sophistication is unlikely. All the same, several of the oldest stones surrounding the monument provide interesting alignments. These two mark the setting point of the midsummer sun. Intriguingly, they also mark the setting point of the midwinter moon. To the ancients, the sun and the moon were easily predictable. Wandering stars were not. The bodies we know today as planets. Planets appear to wander because, like Earth, they're orbiting the Sun. They don't move in unison with the background stars. The Greeks saw the universe like this, a series of concentric crystal spheres, all in motion around the Earth. Within each sphere was set an orb, the Sun, the Moon, and the 5 planets known at the time, those wandering stars. The outermost sphere was the realm of the background stars. It was a neat model, but it didn't explain the eccentric movements of the planets. Why, if they were carried in crystal spheres, did they sometimes go backwards? The Greek astronomer Ptolemy had an answer. He worked in Alexandria in the 2nd century and firmly believed that the planets orbited Earth. He accounted for the wanderings with the idea of epicycles, little circles described by the planets around their main orbital paths. It was a clumsy notion, but it fitted the observations. On Midsummer's Day each year, the sun would shine directly down a well at Aswan in Egypt. This was known to a librarian called Eratosthenes. He worked several hundred kilometers to the north in Alexandria. There, at the same time, a column cast a shadow. He wondered why. The reason is the curvature of the Earth. As sunlight falls vertically on the well in Aswan, it's at an angle in Alexandria. Geometric calculations gave Eratosthenes the circumference of the Earth. He'd noted that the sun was off vertical in Alexandria by 1/50th of a circle. So, by multiplying by 50 the distance between Alexandria and Aswan, Eratosthenes got the globe's circumference. He was within a few percent of the right answer. It was 200 BC, 1700 years before Columbus set sail. The brilliantly accurate observations of Tycho Brahe and the sun-centered theory of Copernicus led to the 17th century breakthrough of Johannes Kepler of how the planets orbit the sun. Kepler's calculations had Earth and the planets moving in slightly elliptical orbits. The theory of Ptolemy, which had persisted for 1800 years, was finally disproved, and Kepler's work held good for comets and moons. Galileo backed the idea and was condemned by the Church. His use of the telescope, however, marked him as the first great telescopic observer. At the end of the 17th century, Isaac Newton not only split light into the colors of the spectrum, but he worked out the theory of gravity. Newton showed how objects launched from a mountaintop would fall to Earth through gravity, unless they had sufficient velocity to put them in orbit, like the Moon around the Earth, and the Earth around the Sun. In the 19th century, William Herschel built a big telescope and began the mapping of the sky. He was the greatest visual observer. The 20th century brought huge instruments that probed far into the heavens. The astronomy of deep space had begun. The past 100 years have revealed the nature of stars. Astronomy has unveiled the great collections of stars we know as galaxies. How there are millions and millions of galaxies, each containing billions of stars. And how galaxies form great strands that float in the emptiness of space. Far from being at the center, astronomy has shown us to be a mere speck in the cosmos. As galaxies are the building blocks of the universe, so stars are the molecules in those blocks. But what are stars and how do they form? Our nearest example is the Sun, a gaseous inferno, a cosmic compromise between nuclear forces blowing outwards and gravitational forces pulling inwards, a balancing act that will eventually wobble. $15 billion years ago, in the maelstrom of gas and dust that followed the Big Bang, the first stars took shape. They preceded the first galaxies, for without stars, there can't be galaxies. These early stars began to group together. Some may have survived to this day. Globular clusters, as they're called, are to be found orbiting over the center of galaxies, galaxies which formed long after the clusters. Galaxies were born 1 billion years after the Big Bang. This one has 1 million stars. And this one has 1 million stars. A galaxy grown fat by gobbling up others. The process can be seen today. Here, 2 galaxies in the act of a heavenly merger. A more modest galaxy, the irregular form of the Large Magellanic Cloud. And a spiral galaxy, shaped like the letter Z. With 200,000 million stars in its sphere, this spiral is more tightly wound. It's a typical medium-sized galaxy, not unlike our own, the Milky Way. In simulation, this is an edge-on view of the Milky Way. The globular clusters, a yellow halo around the center. Their ancient stars are between 12 and 15 billion years old. Our own star, the Sun, is much younger. It formed 4.5 billion years ago and lies in a spiral arm towards the edge of the galaxy. It's nearby that stars are conceived in a vast bubble of hydrogen. We can see it from Earth in a neighboring arm of the spiral within the constellation of Orion. Inside this cloud of dust and gas, matter is squeezing ever denser. Gravity increases, temperatures soar, nuclear fusion begins, and stars are born. This is a photograph of that stellar nursery, M42, the great nebula in Orion. In the 90s, the region came under the powerful scrutiny of the Hubble Space Telescope. For the first time, we could glimpse hot new stars surrounded by great disks of material. In the case of our Sun, it was such a disk that evolved into the planets. The Milky Way is full of places where stars are born. It was in a dark area like this, a Bock globule, where the Sun first shone. Jolted possibly by a nearby explosion, a cloud condensed to become our star. Settled now into comfortable middle age, the Sun shines yellow with a surface temperature of 6,000 degrees Celsius. And that's how it'll be for the next 5 billion years. A nuclear reactor steadily converting hydrogen into helium. But when the hydrogen runs low, our star will begin to die. Desperately, the Sun will start to fuse helium. It'll change color, and it'll grow. Mercury, Venus, and Earth will be consumed. The Sun will be a red giant, its nuclear reactor out of control, an unsustainable situation. Finally, its fuel spent, the sun will slowly collapse. Then, over a prolonged period, material will be puffed into space. The sun itself will be a corpse, a white dwarf no bigger than Earth, so dense that a sugar cube of its matter would weigh a ton. Such a relic can be seen in the constellation of Aquarius. It's called the Helix, a nebula wafted out by a dying star. But here are the remnants of a more spectacular death, the nebula of a gigantic star, blown apart by a cataclysmic explosion. Astronomers call it a supernova. The materials in these vast nebulae have played a vital role in our galaxy, for it's only the biggest stars with over 8 times the mass of the sun that go out with a bang. Were it not for supernovae, we'd have no heavy elements, no iron or precious metals, or the phosphorus and sulfur vital to living cells. In our own galaxy, many giants are destined to go supernova. One of them is Rigel in Orion, 50,000 times brighter than the sun. And in the same constellation, the great star Betelgeuse. It'll go within the next 10,000 years. Superstars are formed from superclouds. The process is like the birth of the sun, just bigger. A massive nebula of gas and dust condenses. As it falls in on itself, gravity increases, temperatures soar, and a nuclear furnace fires up. Because it's so big, perhaps 100 times the mass of the sun, the superstar burns fierce and bright. Enormous gravity at the center creates prodigious heat. As a result, the star can fuse a gamut of fuels at an incredible rate. But its life will be short, maybe just 10 million years. In middle age, the superstar spreads. It gets cooler and redder. At the center, helium is converting into the heavier elements. When iron is formed, energy is no longer being created, but absorbed. The red giant collapses. The resulting explosion is a supernova. As material is shed into space, and providing the giant had been big enough, a remnant remains. It's a neutron star, rotating once every second. Just 30 kilometers wide, a pinhead of its material would weigh 1 million tons. There's a neutron star in the Crab Nebula. It can be seen optically, its twin magnetic beams pulsing like a lighthouse. A red giant in cross-section reveals the anatomy of a catastrophe. As it ages, the giant fuses more and more elements, not just hydrogen and helium like the sun, but heavy metals. They form internal shells. An iron core is created only to collapse and explode. It's supernovae that have seeded the universe. They've distributed the heavier elements and provided the basis for life. If the surviving core of a supernova is more than 3.5 times the mass of the sun, then it'll collapse beyond the stage of a neutron star. It'll become a black hole. the Milky Way is rather bigger than the average galaxy. Astronomers estimate it contains some 200,000 million stars. They orbit the galactic center, among them our own star, the Sun. In isolation, the Milky Way is like a separate universe. But travel away, and it's just one member of a local cluster of galaxies. In turn, these clusters form strands. Like dewdrops on a spider's web, each point of light is a galaxy cluster. Each cluster contains hundreds of thousands of galaxies. Figures become meaningless. This is the structure of the universe. Strands of galactic matter strewn through unimaginable emptiness. The further we travel, the further we return in time. For as we shall see, in astronomy, time and distance are linked. To understand distance is to begin to know the universe. With time running backwards, we're looking at the primeval gas clouds that spawned the stars and the galaxies. We're back 15,000 million years. This compact ball is all there was of the universe. We're in slow motion. These are the moments immediately following the instant when time and space began. The Big Bang. Time is running forward, an explosion from a pinpoint that began everything and continues today, ever expanding. But how do we know this? Astronomers began by learning to measure the universe. From Earth, an observation is made of a nearby star. Then from the opposing side of our solar orbit, a second observation. Between the two, taken 6 months apart in space, the star will appear to jump against more distant objects. The width of the shift gives its distance from Earth. The method is called parallax, but it only works for the stars nearest Earth. Space-age astronomy can measure the cosmos. The European satellite Hipparcos is systematically scanning the heavens. Its data will fix distances as never before, and an exact dating of the age of the universe may well emerge. The color of stars and the spectra they display tell us much about them. Analyzed in a spectroscope, starlight is a fingerprint. Among other things, it reveals temperature. Spectra fall into groupings, categories which relate a star's temperature to its brightness. A yellow star, like our Sun, has a brightness rating of 1. More brilliant stars shine blue, rating 10, or 100, even 1,000. If the temperature of a star is known, then its brightness rating gives its distance. For instance, if we know from its temperature reading that the big star on the left is 100 times brighter than the star on the right, then why do they shine with equal brilliance? The answer is that light diminishes by the square of the distance it travels. So in reality, the big star is 10 times further away than the little star. Again, the method is good only for objects close by. How can the distance of a remote galaxy be measured? The discovery of a type of variable star called a Cepheid offered a solution. A Cepheid is slowly pulsing yellow in the right-hand side of this galaxy. Now, because the Cepheid is bright and distinguishable, its period of variability can be easily measured. From this, astronomers can calculate its true brightness. That gives them its distance, and therefore the rough distance of the galaxy. Here's a Cepheid flashing in a galaxy 16 million light-years away. Pictures from the Hubble Space Telescope. As stars can be fingerprinted and studied, so galaxies yield information through their spectra. The further the black lines in this spectrum move towards red, the clearer the message that the galaxy is retreating. It's called cosmological redshift. As the universe continues to expand, all galaxies are in red retreat. A light beam could travel around Earth 7 times in a second. It could reach the Moon and back in 2.5 seconds. From the Sun to Earth in just over 8 minutes. Right through the solar system in 5 hours. From the Sun to the nearest star, 4 years and 4 months. To the galactic center, 30,000 years. Across the galaxy, 100,000 years. The distance can be expressed in light years. To the next big galaxy, it's 2.5 million light years. To the edge of the known universe, 15 billion light years. In such vastness, miles and kilometers make no sense. Only light years can hint at the distance to the galaxies and the turmoil therein. These pictures of galactic unrest are images from the past. They're from the Rosat X-ray satellite. If they took 1 billion years to reach Rosat, then the turbulence they portray happened 1 billion years ago. Galaxies aren't the serene structures once thought. They bump into one another. Here are two in the process of a gigantic galactic merger. This pair is in a gentler encounter. A computer forecast has them go their separate ways. How they unraveled each other is clear in reverse. A picture from Hubble of galaxies about to meet. It's increasingly accepted that this sort of interaction is an important part of galactic evolution. A galaxy in the constellation of Virgo is seen here as a combined optical and radio image. In the early 90s, its center was probed by Hubble. Hubble revealed a cloud of swirling dust. It surrounded what's probably a black hole. In animation now, this could be the scene. Like water down a plug hole, material is whirling towards an irresistible focus of gravity. Nothing, not even light, can escape. This is a black hole. Black holes may power quasars. Largely a mystery, a quasar is the ultimate concentration of energy. 100 times brighter than a galaxy, yet no bigger than the solar system. Technology, like the COBE microwave satellite, is unlocking the secrets of the universe. When COBE took the temperature of the universe, it picked up the background radiation of the Big Bang. In doing so, it confirmed that there had been a moment when time and space began. More recent measurements in X-ray suggest there'll be a moment when the universe ends. A cosmic contraction finishing in a big crunch. A portrait of the Horsehead Nebula in Orion, a photograph through one of the most powerful and sophisticated instruments on Earth. It came from here, the 1.2-metre Schmidt on Siding Spring Mountain in New South Wales. Operated by the Anglo-Australian Observatory, the Schmidt is the biggest telescopic camera, resolving the finest detail in the Southern Hemisphere. A cosmic eye, requiring huge photographic plates, sheets of light-sensitive glass that may be exposed for hours. Schmidt colour masterpieces are produced by photographing the sky on 3 occasions, each time using a different filter. And here's a portable version, for it's just as likely that the amateur will be setting up for an overnight shoot in the outback. These photos of Halley's Comet were produced with such equipment: a small telescope and a Schmidt camera with a wide-angle lens. For pin-sharp pictures, the photographer must track the heavens. In this long exposure, the camera had locked on to the motion of the stars. And this is time-lapse, where a special static camera takes an exposure once every 30 seconds. The stars turn because of Earth's rotation. Do the same with an ordinary camera, but leave the lens open for a few hours, and the result is star trails. These ones are circular because the camera was looking at the southern pole of the sky, the red glow from a rare Australian aurora. This is 2 exposures, a quick one for the star point, a few hours for the trail. And here the camera has been progressively refocused over a long exposure. A pretty effect, revealing the true colours of stars. Mounted between the camera and the tripod is an automatic drive. It compensates for the spin of the Earth and keeps the camera locked on to its moving targets. Using such a drive, a long exposure achieved this picture on low-speed film. With very fast film, a drive is unnecessary. By holding the shutter open for 30 seconds on a cable release, anyone can capture the cosmos. Here's the Andromeda Galaxy, the most distant object visible to the naked eye. And the constellation of Orion from the southern hemisphere, another 30-second exposure. The 2 Magellanic Clouds, our satellite galaxies. One of them in close-up, again on high-speed film. A little art, the stars through the glow of a terrestrial volcano. Another in Hawaii, all with a regular 35mm camera. A little house beneath the stars. The trick was to use a flashlight on the bungalow during a 30-second exposure. The same here, and in the sky at the top, Halley's Comet. Astronomy is a science which lay people can share. That's its joy. The first stop for the serious amateur observer should be a reputable telescope shop. But before deciding on a purchase, the enthusiast should seek advice, for the array of instruments is tantalizing. This is a typical beginner's telescope, a refractor. For stability, it's mounted on a stand. A refractor gathers light from the stars through a large lens. The image is focused at the other end of the tube and magnified in the eyepiece. It's the amount of light gathered that's important, not magnification. An alternative starter is this reflecting telescope. Again, it's the capacity to gather light that matters. Incoming light hits a mirror at the bottom of the tube. The light is bounced to a smaller mirror and reflected to an eyepiece on the side. This manual drive is a handy accessory to keep a telescope on track, for Earth is always turning. A motor drive is necessary for bigger telescopes. Their greater magnification calls for finer tracking. Here's a Dobsonian, a simple low magnification reflector, but pulling in lots of light. And it's relatively inexpensive. This one is a telescopic hybrid, part reflector, part refractor, lens and mirror synthesizing a superb image. A small instrument with a big performance, the stylish and intriguing catadioptric. There are smaller versions, no bigger than a camp stove and equally portable, a mighty eye on the sky for the mobile observer. And here a filter to turn a personal telescope into a competent solar observatory. With the filter and other safety devices attached, movie of a solar prominence. Also through a small telescope, the surface of the sun. Shots so defined they wouldn't shame a professional. And again, using a solar filter, a partial eclipse of the sun. An eclipse brings out the most exotic equipment. Giant filters to protect both telescope and camera, and most importantly, the eyes of the observer. The results can be awe-inspiring. But they can be had only through filters, whether expensive optics or the simplest device. The wrong way and the right way to shoot movie of an eclipse. One is handheld, the other is rock steady on a tripod, even with a telephoto lens. The lack of a telescope is no bar to astrophotography. This is an eclipse of the moon shot on a 35mm camera in central London, amid massive light pollution. And here, a partial eclipse of the moon, a touch romantic. The moon with 3 planets, Jupiter, Saturn and Venus. And a young moon with Venus. As the great modern telescopes collect images from the cosmos, they're stored on CCDs, electronic chips, the tool of the professional astronomer. No more, the CCD is now available to amateurs, and the sky's the limit. A distant cluster of stars on amateur CCD. The nebula of a dying star, amateur CCD. Craters on the moon, amateur CCD. A remote galaxy, amateur CCD. But for all the advances in technology, there's emerging a more traditional way for the lay person to capture the cosmos, the developing genre of space art. This is a planetarium, a showplace of the stars. From the Big Bang to the most exotic stars, the cosmos in microcosm, from the comfort of a theatre seat. The London Planetarium in England is one of the most popular in the world. As the effigy of Albert Einstein testifies, this is a famous spot. Together with Edmund Halley, the astronomer, they survey the patrons. For the London Planetarium runs in conjunction with the waxworks of Madame Tussauds. Typically of planetaria, a space and astronomy hall complements the theatre. Information as entertainment, and none the worse for that. Facts and figures at your interactive fingertips. This is a classic planetarium projector, an electromechanical masterpiece developed by Zeiss in Germany in the early 1920s. It comprises clusters of small projectors. As pinpoints of light, each cluster reproduces a segment of the sky on the planetarium dome. Dubbed the Wonder of Jena after the city of its origin, the very function of the machine became a star turn. As it whirs and rotates, the projector can simulate the stars and their movements as seen from anywhere on Earth. After 70 years, most planetaria still use a projector of this basic design. A latest version employs fiber optics, a refinement to ensure the most accurate reproduction of the night sky. Even so, the projection achieved is still two-dimensional. The stars in motion across the heavens. It's a limitation of the electromechanical projector, however good. Enter the special effects department. To put the oomph into star shows, the best planetaria have an array of auxiliary projection systems. Slides, video disc, all synchronized with the main starball projector. The resulting shows can be an astronomical delight. And if you can't make it to a planetarium, there's always the carry-away version. A box containing the projection system, and for the audience, the fun of a light-proof inflatable dome. Ideal for schools or anyone remote from a city venue. This city venue is American, the Carnegie Science Center in Pittsburgh, Pennsylvania, a planetarium for the 21st century. At its heart is a new projection system. It works like a television tube. Instead of the starball, a silent and unobtrusive lens throws a cathode ray image, a picture with an extra dimension. The system is called Digistar. It was developed in Salt Lake City by a company specializing in computer simulation. But Digistar is only as good as its programs. Like a starball, it can accurately reproduce the night sky. Its advantage is this: the ability to move through space and through time. How the cosmos was and how it will be. Digistar is capable of any dot or line rendering, whether it be a star field or shuttle in Earth orbit, setting aloft the Hubble Space Telescope. Digistar, with special effects and a good producer, can transport you to that final frontier. Seville, Spain, to a planetarium with an extra ingredient. During the 6 months of Expo 92, this theatre packed in record-breaking audiences. They were served a cosmic cocktail, high-resolution TV graphics combined with star fields and the movement of digistar. The computer renderings offered what digistar couldn't, solid images in color. Patrons see them on film and television, so why not on the planetarium dome? Plus, of course, the excitement of all-enveloping, wrap-around sound and vision. And the ultimate trip into a black hole. The Seville system has been adopted by a new planetarium in Stockholm, Sweden. As with many planetaria now, it's a steeply raked theatre with a tilted dome. It can also double as a big screen cinema. A gigantic image is thrown onto the dome by an Omnimax film projector. It slides into place from beneath the audience. Visit the planetarium nearest you. A good astronomical picture is worth 1,000 words. For a more tangible venue, the Kennedy Space Center in Florida. A bus ride will take you past the most famous launch sites in the history of American rocketry, including, of course, the ongoing program of Space Shuttle. Every few months, a shuttle lifts off from this pad. In front of Shuttle's assembly building, the enormity of the famous Saturn V rocket. Laid out stage by stage, it was this Saturn series which carried men to the moon. Where once Saturn was built, NASA's vertical assembly building now sees Shuttle gently rolling towards the launch site. If you hit the right day, you can watch a blast-off 15 kilometers from the pad. And with things freed up in the former Soviet Union, a Russian launch like this can now be viewed in Kazakhstan. For history buffs, there's the wonder of Stonehenge, a megalithic observatory in England. And further back, the crater punched by a meteor in Arizona 25,000 years ago. In the Australian outback, the fossil of an even older meteor crater at Gosses Bluff. Most astronomical institutions have visitor centers, like this observatory in New Mexico, the radio dishes of the Very Large Array. In England, at the radio telescopes of Jodrell Bank, you can operate your own dish and visit a planetarium. Optical observatories like Kitt Peak, Arizona, welcome visitors. So too the Anglo-Australian Observatory in New South Wales. But for aspiring astronauts, this is the place. Space Camp. A vacation where for a few days you can live, eat and sleep as a space person. And it's not just for kids. Adults can maneuver propulsion units and learn the basics of space science. In America, there are highly successful space camps in Florida and here in Alabama. Now the Russians are following suit. From underwater spacewalks to piloting the shuttle, a chance to experience the nuts and bolts of working in space. The thrill of shutting the airlock, a job well done. Another day in the life of an orbiting astronaut.
The unit Astronomy and the Stars is available on video, priced £10.99. The Teacher's Guide at £3 contains programme summaries and background information. To buy these items by credit card, please telephone 019